Hello and welcome to COMS1202 Methods and Problems in Computer Science. My name is Mark Santolucido and I will be your professor for this class. I just wanted to take this time to give a short introduction to what we're going to be focused on over the next 6 weeks. You have a bit of a sense of what you're getting yourself into. So this class is going to be looking a little bit beyond computer science as computer programming. And we're going to be really looking at the science aspect of computer science. What do computer scientists do? What are the problems they care about? What are the methods that they implement? My hope is that by the end of this class, you will have the skills and the knowledge and the vocabulary that you need in order to talk with the computer scientists about the problems that they're working on today and have some interesting conversations. So I should note, this is a Intro to Computer Science for Non-Majors class. So if your plan is to take this class and then go major in computer science, of course, you're welcome to do that, and I hope you might consider it. But this will not count for your intro class, so you'll still have to take COMS1004. If you're simply interested in getting an overview of the field and having some idea of what computer science really means, getting your hands dirty with a little bit of programming, then this may be the class for you. So let's jump into the content a little bit. We're going to start our journey in the 18th century city of Königsberg, where there was a city here with 7 bridges connecting these 4 separate land masses. And one of the popular questions that the residents of Königsberg were asking at the time was, is there any way to go for a walk in this city and cross each bridge exactly once? So you can never cross a bridge twice. And this was a problem that stumped everybody for a long time until the problem was abstracted. So rather than looking at the problem as, well, let's actually just go out and walk across this bridge and test out all the different paths. A mathematician named Euler, same Euler you might know from calculus, came along and said, well, let's not look at this problem as a problem that's specific to our particular city, but let's abstract the problem a little bit. Let's look at this problem as a graph. And this is the kind of graph that computer scientists work with, not the plot, the XY coordinate sort of thing. It's something separate. This is a graph with nodes and edges, where the nodes, these yellow boxes, are the land masses. They represent an abstraction of the land masses. And the edges, little gray lines, are abstractions of the bridges. And now we can work on this problem at our desk without having to walk all over the city and tire ourselves out. So this will be the first week. We'll be looking at what is a graph, how do we abstract away from our concrete problem and try and think a little more generally about the problems we're trying to solve in computer science. Then we're going to switch to looking at algorithms. We're going to be looking at, in one example, sorting. And we're going to ask the question, why is it that some of these sorting algorithms are faster than the others? Why does one sorting algorithm complete more quickly than another sorting algorithm? And so what we're going to do is try and find a way to quantify that, to say very precisely why it is that one algorithm is better and where that goodness comes from. And this is a problem that computer scientists spend a lot of their time working on. Then, once we've been looking at sorting algorithms and comparing algorithms for solving the same problem to each other, we're going to take a step back and say, how do we compare algorithms that solve different problems? Or how do we compare the hardness of problems themselves? So here are 2 different algorithms for solving what's known as the traveling salesman problem. You can see the one on the bottom finished a bit quicker than the one on the top. And we already have a way of comparing these 2 different algorithms for this one problem, but the question we'll ask in week 3 is, how do we compare how hard this problem is, the traveling salesman problem, to how hard it is to sort? Is one problem somehow fundamentally harder than the other one? And if so, how do we quantify that? And we'll see This traveling salesman problem is what's known as NP complete, which means if we could find a good way to solve this problem, we could actually find a good way to solve all kinds of other problems in the world. So that will be our first 3 weeks, focused on algorithms and how hard they are. We'll have a midterm in week 3, at the end of week 3, and then in week 4, we're going to shift gears a little bit. We're going to start to think about the implications of the hardness of these problems. In particular, one thing that's really important is security. And we'll look at, okay, well, we said these problems are really hard, but that was based on one model of computing. What if we had a different model? So we're going to take a quick look at quantum computing. And here you see a bit of a nice animation for transforming a classical computing circuit to a quantum circuit. And we're going to ask, what are the implications of quantum computing? What is quantum computing first? And what does it mean if we had different ways of approaching these problems? What would the implications be in society for us? That'll be week 3. Week 4, we're going to look at programming languages. And we're going to say, let's look at programming languages a bit more, again, abstractly than just text on the page. We're going to say, can we look at programming languages as mathematical objects, just as we looked at the city of Königsberg as a mathematical object, as a graph, rather than a specific city. Here we're going to look at programs as, rather than the specific lines of code, the characters that have been entered into your text editor, we're going to look at those programs as mathematical objects and say, what can we learn from looking at a more abstract version of our program? So here on the top, you see an animation of how we evaluate a program. So we're going to really dig into how programming languages are constructed and what it means for a programming language to compute. Then finally, in our last week, we're going to look at general models of computation. Here you see this is Conway's Game of Life, and these are little gliders that are being constructed, and there's a set of rules that are governing how all these little particles seem to be moving around on your screen, and this is actually a model for computation. And so we're going to look at Conway's Game of Life, as well as other models of computation like automata and Turing machines that you might have heard your computer scientist friends talking about. And we're going to dig a bit into those and try and understand, what is all of this stuff? What does it mean, and why do we need to care about it? So those are the topics at a very high level that we're going to be covering. So let's just take a quick overview look at the class schedule. So as a reminder, this class will meet Monday, Tuesday, Wednesday, Thursday from 1 to 2:35 Eastern Time on Zoom. So go to Courseworks to find the Zoom link. And a bit about the homeworks. This is going to be an experimental homework style class. So Monday, Tuesday, and Wednesday, we have practice problem focused homeworks. So those are going to be coding homeworks and homeworks from the textbook. Then on Thursday to Sunday, we're going to be focused on group work, doing content creation. So we're going to break into groups based on whatever it is that you're interested in. So we might have a group that is computer science for psychologists, or a group that's computer science for musicians. And each weekend, you're going to choose within your group one topic that we covered in class that you found interesting, and you're going to create a YouTube video, kind of like this one, that you'll present to other people who are interested in the same thing you are. So we talked about the Conway's Game of Life. You might come up with a YouTube video that's Conway's Game of Life for psychologists, or Conway's Game of Life for musicians. And that will be the rhythm of the class. Monday, Tuesday, Wednesday, building that foundation, getting our hands dirty with coding and practice problems from the book. And then Thursday through Sunday, we're going to be really directly practicing the learning goals of this class, which is to be able to speak intelligently and with a deep knowledge of the computer science topics that are relevant to today's world. So that's the high-level overview. I'm looking forward to this class. It's going to be a lot of fun for me to teach, at least, and I hope it will be a lot of fun for you to be a student in. So I'm looking forward to seeing you all on Monday, and I'll see you then. Bye.